Hello everyone, my name is Yuting Song from University of Connecticut. Today I'm going to talk about my paper Parameter Identification for Synchronous Two-Machine Exponential Production Line Model. First, I will give a brief introduction of the background. With the development of Industry 4.0, model-based analysis plays more and more important role in manufacturing research. We build wild models to capture the behaviors of job flow in production systems, and then the model-based analysis supports our smart production system. So using the models, we can make decisions to optimize the production process for some different kind of objectives, such as increasing productivity, increasing the quality of production, allocation the resource to reduce the total cost and energy, rapid reaction to change, advanced planning and controlling, and so on. Thus, modeling is essential to model-based analysis into smart production system. In the process of modeling, parameter identification is one of the most important steps, and this paper focuses on parameter identification. In conventional approach, we first build structural models based on the system layout, and we collect data from each individual workstation in the physical level, and come up with methods to aggregate data and to extract the model parameters for individual process and step parametric models, and finally obtain the overall system model. There are many limitations. First, for some small and medium-sized manufacturers, they do not have any automatic data collection equipment, so data collection is difficult to them. Then, in order to get valid machine parameters like the uptime, downtime for each machine, we have to spend a long time on connecting many enough observations to make sure they are in a high accuracy. And the data we collected is not necessarily in the standard form, so a lot of inconvenient data process work is involved. Finally, there is no standard rule or unique solution to aggregate data or extract the model parameters, so it requires a lot of modeling experience and training of modelers. Therefore, we want to develop a new approach to solve these limitations. In our new approach, we use standard performance metrics data to identify machine parameters instead of those non-standard form data. So our goal is obtaining the parameters which are the best match with the system performance metrics. Moreover, the new approach is much more efficient and convenient because performance metrics data is very easy to collect on factory floor in a short time, and they are commonly used and easy to understand. In addition, the user just need to give the performance metrics as an input, and then they will obtain the machine parameters as output without doing anything else. Everyone in different knowledge level can handle it easily. In this paper, we focus on synchronous exponential production system. In the figure, it shows the simple case. Only two machine and one buffer. We assume the downtime uptime of the two machine follow exponential distribution, so there are four parameters of this system. Lambda is the breakdown rate and mu is the repair rate, and we can get the machine efficiency in terms of lambda and mu. On factory floor, the machine parameters are unknown. In order to build a valid model, we have to find the machine parameters which fit the mean characteristics of the real system. However, the downtime and uptime of machines are difficult to measure directly on factory floor, but the data of performance metrics such as production rate, working process, probability of empty buffer, and full buffer in steady state are very easy to collect. So we can use these performance metrics to identify the machine parameters. In existing literature, we already have the analytical expression of the performance metrics in terms of lambda and mu. Theoretically, given the four performance metrics, we can find lambda and mu by solving the equation system. However, their expressions are so complex that it is difficult to find the analytical solution, so we search the numerical solution instead. So we define the vector-valued function f and identify machine parameters by solving following constraint optimization problem. We minimize the two-norm error between the performance metrics calculated by identified parameters and the true value of the performance metrics under a constraint set X, where X is the set containing all possible values of lambda and mu. To solve this constraint optimization problem, the first approach we develop is parameter. We rewrite the original problem to the form 1 and add the log barrier function in terms of constraints. So the constraint optimization problem is transformed to the n-constraint one. Under a certain t, we can get an optimal solution. We iteratively increase t and improve the optimal solution until the expected accuracy is reached. So the basic step of parameter is as follows. First, we randomly select the initial point in the constraint set. Then, we solve the unconstrained problem using BFGS Coarse-Newton method and update t by multiplying a barrier parameter, gamma, and use the optimal solution under tk as the initial point to solve the unconstrained problem under tk plus 1. We repeat this iteration until the solution converts to a wanted accuracy. In the central path, the gradient is involved in BFGS Coarse-Newton method. The expression of the objective function is too complex to obtain a closed form of gradient, so we use the central difference formula to approximate the gradient. This method is gradient-based, so the issue is if our problem is not convex, we may get a local minimum. Next, another non-derivative method is also developed. Another algorithm is cyclic coordinate descent method. The basic idea is solving a series of one-dimensional problems to update the lambda and mu until the value of objective function is very close to zero or cannot be decreased. Here we use Gaussian method and a proximum point update to guarantee convergence. With an initial point for each subproblem, the unique minimum exists because of some empirical properties of exponential production line model, so golden section method is used to find this minimum in a certain interval. Therefore, no gradient or derivative operation is involved in this method. In existing literature, coordinate descent method is proved having better convergence property. However, the iteration process may be very long due to its sublinear convergence rate. In numerical experiments, the performance of these two methods are compared and illustrated. We randomly generate 10,000 exponential lines, and both theoretical and simulated performance metrics are calculated. Given the performance metrics, the algorithms are applied to obtain the estimated parameters, and we use an optimality tolerance to detect the convergence to a local minimum. Besides our proposed methods, we also compare them with a multi-heuristic optimization algorithm, genetic algorithm, which can generate high-quality solutions to a constraint optimization problem. Moreover, to evaluate the solution obtained by our algorithms, we compared following two types of estimation errors. First is the estimation errors of machine parameters to compare the estimated parameters with the true parameters. And the second is the estimation error of performance metrics to understand how well the estimated parameters fit the given system performance. In numerical experiments, first we use theoretical performance metrics to identify the parameters. Without any effect from data noise, this experiment can demonstrate the exact performance of an algorithm itself. For the gradient-based measure, parameter, there is a risk at the local minimum, which can be indicated by setting an optimality tolerance, which is represented as the dashed line in the figure. By changing the initial points, some cases can reach the global minimum eventually. However, finally there are 5 cases out of all 10,000 cases with the invalid solution, which are the local minimum after 500 different initial points are tried. Using the coordinate descent method, all cases get the valid solution, and more than 1,000 invalid solutions are obtained by genetic algorithm. Furthermore, barrier method has the highest accuracy in both estimated parameters and performance metrics. The similar numerical experiments are implemented based on given simulated performance metrics. Due to random noise in the simulated performance metrics data, the estimation error increased significantly compared with those based on theoretical data. The accuracy of our proposed method are close, because the random noise in simulation becomes a dominant factor in affecting the accuracy rather than algorithm itself performance. The genetic algorithm still has larger errors than our proposed methods. Comparing our two methods, barrier method converges faster. The computation time of each case is about 0.08 seconds on average, but it has a risk of local minimum. In the experiments, with the different initial points, finally local minimum are still obtained for about 3 to 5 out of 10,000 cases. On the other hand, coordinate descent method converges slowly. The computation time is about 42 seconds on average, but in experiments, global minimum are obtained for all cases. So we can do the symbol strategy to guarantee a global minimum in an acceptable time. With the optimality tolerance to indicate a local minimum, we first use barrier method. For each case, we set k chances are allowed to change initial points if local minimum is indicated. After k tries, we use the coordinate descent method to solve those unsuccessful cases. For conclusion, in this paper, we study a parameter identification problem in production system modeling. Given the steady-state production rate, working process, the probability of empty buffer and full buffer, and their analytical expression in terms of machine parameters, we solve the problem of performance metrics data-based parameter identification in Synchronous two-machine exponential line model. We formulate this parameter identification problem as a constraint optimization problem and search for the optimal combination of machine parameters that best matches the given system performance metrics data. To solve this problem, two optimization algorithms are developed. Barrier method with BFGS, Coulson-Newton algorithm, and cyclic coordinate descent method with proximal point update. With the proposed algorithms, the average estimation accuracy in both machine parameters and performance metrics are very high. To balance both computation efficiency and convergence to the global minimum, an ensemble strategy is recommended. In future work, we can extend this research to more complex production system models, such as multi-machine serial production lines, systems with asynchronous machines, systems with assembly operations, rework loops, and so on. Thank you.